Alright, what we have here is an example of a shock wave. And the shock wave is actually, and let me see if I can just pause this for a moment. There we go. So the shock wave is actually this right here. And you can see it in this direction as well. And it's called a shock wave because the pressure involved is very, very intense. And I should say the pressure differences are very, very intense. So you end up with very, very low pressures followed by very, very high pressures, or vice versa. And you can see that what makes it a shock wave, what makes it kind of a wave on its own, is that the wave fronts, the crests, so to speak, from each vibration that took place. As we track back, we can mark where the vibrations took place. So this wave out here took place from a vibration that was maybe somewhere right in here. Well, they're all taking place in such a way that the wave fronts are lining up with each other. If I slow this down so that the speed is much less than the speed of the sound waves in the medium, you see that there's no building up of the wave fronts. They get close together, but they never actually build up with each other. Once we hit Mach 1, now we can see that there is this building up, this adding up of waves right on top of each other. The reason for this is because now the source of the sound waves is traveling at the exact same speed as the waves themselves. So the waves can't actually get out in front of it at all. And so what ends up happening is it creates the shock waves, or the wave fronts, the crests, let's say, at the same position that all of the previous wave fronts are now located. And that causes constructive interference. That causes the superposition principle to state that the wave fronts will add together because they're lining up with each other perfectly. Right when it's going at Mach 1, which is the speed of the sound waves, it's making an angle of 90 degrees to the direction of motion. As we start to increase this, so I'll run that animation again, and I'll make it go a little bit faster. Now we get something that you might see if a boat is traveling through water. Bear in mind that a boat traveling through water is no different from a sound source producing sound waves in the air or whatever medium it happens to be. Whenever you're disturbing the medium and producing waves, if the source of that disturbance is moving faster than the waves can travel, you're going to get a shock wave. And so if you look at a boat, it produces a wake. That wake is another type of a shock wave. Now what you'll notice though is that as we make it move faster, the angle changes. It becomes more and more narrow. And so if I run this and I just make it go a lot faster all at once, now the shock wave is very narrow. And the reason for this is because the wave fronts are traveling at the same speed as they all have always been. Now strictly speaking, that isn't quite true. They're traveling slightly differently, probably a little bit faster. The shock wave travels than the waves themselves. But for our purposes, we can approximate the wavefront of a shock wave at traveling at the same speed as the waves themselves travel. The idea then is that because the source is moving so much further ahead, the waves are now spaced further apart from each other, and so in the time that it takes them to move and get stacked up with each other, they haven't moved as far out. Now you can imagine that if you're down here standing somewhere, let's say this is a plane going by overhead, and you're down here on the ground standing somewhere, you see the plane go overhead and you hear nothing. Nothing, 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 until finally the wavefront reaches you, and it's going to take a while. So let's imagine that you're standing right here, plane passes overhead, and it takes that long for the sound to actually hit you. And what you will hear overwhelmingly, because the pressures are going to be so great, is instead of hearing a particular frequency very well, you'll simply just hear an explosion. And it'll be like a bang or a snap, depending on how big the object is that's creating the waves. And it can cause damage. This is one of the reasons why they don't allow flight above the speed of sound over residential areas, because it can actually damage the structures of the buildings. It can knock things off the walls, shatter your belongings, because it is very, very powerful. particularly when made by an object as large as a jet or a plane. So we're not going to get into too much of the mechanics of the shock wave, but I do want you to have an understanding of what the shock wave is and how it works. What we're going to do next is look at another example of the Doppler effect. Alright, in this example we have a person running towards a wall and shouting. Not terribly exciting, but that's what this person is doing. And what we want to do is figure out what frequency does the person detect. So we'll say that the person is emitting a frequency of, we'll go with 400 hertz again, it's a nice number. So we'll say 400 hertz is the, I did that a little bit wrong. So that's actually our original frequency that we want, 400 hertz. And we want to know what is the frequency that is detected by the person. So the first thing that we should recognize is that the sound waves coming towards the wall are going to be squished together. So if I draw some of the ones behind, they're going to be further apart. What's going to happen though is that when they hit the wall, they're going to bounce off at the same frequency that they entered in. So they're going to come back at that same frequency, not that he was producing them at, but at which they hit the wall. Now, why this is an interesting problem is because the person is running towards them. So we actually have two separate Doppler problems. In the first problem, we're looking to see at what frequency does the wall detect the sounds. So you can imagine maybe there's somebody standing on the side of the wall with their ear pressed up against the wall. That's an ear, by the way, ear. So with their ear pressed up against the wall, listening to the sound that's hitting the wall. So that's the first thing we need to know, because what's going to happen is the wall is then going to reflect the waves at that exact same frequency. It's not going to change the frequency in any way, it's just going to reflect them back. But then the person is going to hear the waves at a new frequency. So the first thing we should do is figure out what is the frequency of the source of the sounds. And we'll say the frequency of the source of the sounds, I'm sorry, not the frequency of the source of the sounds, that's 400. The velocity of the source of the sounds, the original source, is going to be, let's go with the old standby, 5 meters per second. On the other hand, the velocity of the second source of the sounds is going to be 0 meters per second, because the wall is not moving. So we have two different sound source velocities to deal with, one for each case. And I'm going to just underline this one in that color so we know it belongs to kind of the original setup. So that's our case, but then the other thing that's interesting is that this person then becomes the observer. So the observer in the second case becomes a speed of 5 meters per second, but in the original case the observer was not moving at all because that was the wall. Okay, so we have these differences, these different types of problems taking place here, and we have to keep track of what's going on. I could make it a little bit more complicated by saying maybe the wind is blowing in this direction. And you might wonder, well, what would that do? Well, if the wind was blowing at 10 meters per second, let's say, what that's going to do is it's going to stretch the waves forward. It's going to make the waves move faster. Because if I were to tell you the velocity of the waves in their medium is 340 meters per second, but the wind is blowing at 10 meters per second this way, what that's going to do is it's going to carry the waves forward at a higher speed. So they would be detected then at a different rate. On the other hand, when the waves were coming back this way, they would be going against the wind. And so the wind would slow down their rate of motion. And all that you would really end up doing is you'd adjust the speed of the waves. When the waves are going with the wind, you'd make them go a little bit faster. When the waves are going against the wind, you'd make them go a little bit slower. For me right now, that seems like an unnecessary complication. It's enough that you now know at least maybe the idea behind it and could apply it. So let's just start this off, and we'll say v prime So this is detected by wall. So the frequency detected by the wall is equal to the original frequency times V plus or minus V of the observer divided by V minus or plus the velocity of the source. And we can just get rid of this one up here completely because the observer is not moving. It's the wall, it's just staying still. So then we just have to contend with this one, and I'm going to use the minus sign because the source is moving towards the observer. So we're getting the wave scrunched up. And so we'll wind up with that V prime equals, F prime equals F, V over V minus V source original. And then for the next part, you would have V double prime equals, F, I keep saying V, I mean F double prime, so the frequency, this is detected by a person rebounding off of a wall. So this detected frequency is going to be F prime times V plus V observer double prime I'll use here. And that's the velocity of the person, divided by V, and I could do minus or plus V source, but the source isn't moving it. That's the wall now. So without the moving source, this is what we get. And I can plug things in if I'd like. And I can say that the frequency that's heard by the person is going to be equal to the, if I take this and plug it in, I'll get the original frequency, V over V minus Vs, times V plus V observer double prime divided by V. And one of the nice things is that the original velocity, or the velocity of the waves, cancels out in this regard, and now we just have a pretty simple problem. So we look at the original frequency, and we look at the results, the effects that each thing had. Now it would be a little bit more interesting if maybe the wall, maybe it would seem a little bit insane, but if the wall was moving towards the person making the sound, because then we couldn't just cancel things out, at least not necessarily, particularly if the speeds were shifting around. But what we end up getting then is we would have 400 was our frequency times 340 plus 5 divided by 340 minus 5. So essentially we have 400 times 335 over, 345 over 335. And you can calculate this out and see what the effect is. But primarily it's just a rebound pass to this person in terms of the frequency, and it's just the frequency of that person that ends up making a difference in this case.